Hi, I'm Aditya Golatkar. I'll be presenting a paper Mixed Differential Privacy in Computer Vision. All the information contained in a dataset is transferred to the weights of ML model after training. Given a trained model, we're tackling the problem, can we tell if a certain sample was part of the training set? Differential privacy is a mathematical framework which ensures that the weights contain limited identifiable information about the samples used to train the model, which makes sure that an adversary cannot infer much about individual samples from the model output. It is usually quantified by two variables, epsilon and delta. The smaller they are, the better is the privacy guarantee of the underlying algorithm. When differential privacy is applied to practical vision tasks, we observe that the test accuracy drops from 72% to 28%. Surprisingly, if the user just collects a very small amount of public data, for instance 5 samples per class, they can easily outperform a state-of-the-art DP model trained on 13 times more private data. And this is the key intuition for our work. In general, there is very often some public data available. With mixed DP, we want to design a method that is able to leverage such a small public dataset to improve private training. In this setting, we train an initial base model using the public data and then train a perturbation of the model using all the data. We show that this allows us to significantly improve the accuracy of the DP method while maintaining the same strong privacy guarantees. A general private training algorithm consists of the following steps. Firstly, we randomly initialize the weights. Next, at each iterative update, we clip the gradient of each sample and add Gaussian noise to it in order to restrict the amount of information the gradients contain about individual samples. The clipping threshold is generally fixed before training and does not leverage the fact that the gradient norm decreases with training, but a smaller threshold value ensures better privacy but worse accuracy, while the added noise scales with the model size and hence systematically degrades the performance as practical models are large. This inspires ADAMX, a mixed DP algorithm that uses public data to tune and adapt all measure steps of private training. Firstly, we initialize the private model using the public few-shot model. Then, to obtain the private perturbation, we can do better than standard DP training if we incorporate additional information coming from the public data. In particular, we do it by computing an adaptive clipping threshold using the public data, which incorporates the fact that the gradient norm decreases during training. So the clipping threshold is high at the start of the training, which ensures better learning of features, and lower towards the end, which provides better privacy. Finally, we project the gradient on a smaller subspace and add noise in the small subspace, as the utility of a DP model decreases with the size of the gradient. We construct the subspace adaptively using the public data. This gives us the ADAMX algorithm. Now some experiments. In the error versus privacy plot, the red line shows the baseline accuracy of a model trained using only the public data. The green line is the paragon model trained on private and public data without any privacy constraint. We would like ADAMX, shown in pink, to be as close as possible to the green line while also respecting strong privacy guarantees. Indeed, we see that ADAMX outperforms all the comparable models from the literature, for instance, noisy gradient descent NGD and PPGD public-private gradient descent, and can get close to the green line by satisfying a strong privacy requirement of epsilon equal to 3. On the right-hand side, we also plot the robustness to membership inference attacks and observe that lower the epsilon, which is the number on the circle, correlates with better robustness, and ADAMX offers maximum robustness. With the current progress in multimodal learning, public information may also come from other modalities such as label names. We observe that uniformly across all the methods, initializing the model with weights obtained from language embeddings from CLIP significantly outperforms zero or random initialization. Language initialization only contains label information and not the actual images, and thus can be considered as a zero-shot initialization, while public initialization, which also contains visual information about the task, outperforms this. In the figure on the right, we observe that CLIP features outperform the standard ImageNet features, which suggests that the quality of pre-training plays a critical role in DP training, and that multimodal models could be the next step in DP. Finally, we perform a theoretical analysis of the modified variant of an algorithm. In the convergence bound, we show that the excess empirical risk depends on the distance between the optimal weights and the reference. This distance can be reduced by choosing the reference weights using the public data such that it is closer to the optimal than zero. Next, we bound the excess risk and show that having even smaller amount of public data can improve the generalization performance of the private model. To conclude, we show that we can obtain private and accurate models with small amount of public data using ADAMX. We provide extensive empirical and theoretical analysis of the same. However, as a limitation, we only train a linear model on top of pre-trained ImageNet features instead of fine-tuning the whole network, and provide theoretical analysis for a simplified version of the model. Extending the current analysis to overcoming these limitations will be interesting future work.